Okay, we're gonna go a little faster here. Rip through the rest of this stuff. So we finished at V equals IR. This is called Ohm's law. And if we change it around, you have V over I is equal to resistance, and that's why the slope of this graph is your resistance. Because rise over run is voltage over current. That gives you your resistance. And by the way, this is why current and resistance are inversely proportional, because the I is on the bottom. So if you double your resistance, you will get 1/2 the current. Does that make sense? So what if you triple your resistance? 1/3 the resistance. Okay. And if you cut your resistance into a quarter of what it was, your current will go up 4 times. Okay. Inverse inflow. Okay. This is the complicated part. It's actually not that complicated, it's just kind of frustrating. So, what's moving through the wire to create electricity? Trucks. And what are trucks made of? Electrons. Good. Now, if you think of electron flow, electrons will flow out of the negative side. Okay. Why do they do that, by the way? Because they're negative, and negatives don't like negatives, and what do they like? Positive. So they're gonna go around this way, right? But that's not the way we say that current flows. It's confusing, but we say that conventional current, we call it, goes this way. It's the opposite direction. There's reasons for this, which will make more sense if you take Physics 12 and you learn about electric fields. And electron fields are based on positive charge movement. So even though electrons, actually go from negative to positive, we say that current goes from positive to negative. It's partly because Ampere, when he was discovering current, he didn't know about electrons. So he just treated the positive charges as the ones moving. So electron flow goes from negative to positive, but conventional current goes positive to negative. And you just have to kind of remember that. And it's confusing and a little irritating, but we have to just go with it, because it's been like that for hundreds of years, and we just keep it the same. So for our class, current goes from positive to negative. Even though electrons, we know, go from negative to positive, current is the opposite direction. Chiho, does that make sense? Chiho, does that make sense? Yeah, okay. He doesn't even know what I said. What did I say? How could it make sense if you don't even know what I said? Leo, tell him what I said.
Current.
Okay, that's one word. Current. Yeah, good. Karma, which way does electrons flow?
From the negative terminal to the positive.
Very good. Electrons go from the negative to the positive. But Artin, which way does conventional current go?
Positive to negative.
Excellent. So Chiho, what did they just say?
They just said electrons go from negative to positive, and convection currents go from positive to negative.
Good. So if I ask you which way does current go, you say from positive to negative. That's how physicists think of current. Okay, good. Here's a little example. Don't call out the answer, just do it. I'll give you 10 seconds, go. Callum, you better do it in your head. You can use a calculator to do the math. Put your hand up if you have an answer. Right, good. Still thinking. Lizzie's got one. Lucy's got one. Let's go. Angela, what's the answer?
9.
Good. Who else has 9? Good. So we just use Ohm's law, right? It's very simple. The math in this unit is just super easy. That would be volts, yes, thank you. So V equals IR, we know our current. So this is our I, and this is our resistance. And so it's really just 0.75 amps times 12 ohms. And that's gonna be 9 volts. That's it, easy, right? Okay, power. Power is like energy, but it's energy over time. Okay. So we often talk about the amount of power used by different electrical devices. This is often confused with voltage or energy, but they're not quite the same. The amount of energy is different from power, and then power just keeps going. And so if you have the same amount of power for a longer time, you will use more energy. So it's the rate of doing work. So if you have an electric motor that's lifting something, it'll have a certain power rating. And that's the amount of work that it does over time. But the power will be the same whether you lift it up 1 meter or whether you lift it up 100 meters. The power is the same. The energy will be much more if you lift it 100 stories up to a tall building or something. But the power will be the same because it's the same amount of work per second. Okay. Oops. So I don't know if you can see this, but power is work over time. Yes. Angela, what are you saying? Are you explaining this? Or are you just chatting? It's okay. If you're explaining it, it's okay, but it's a little bit distracting. So this is power. Power is work over time. And so work is force times distance, right? Does that make sense? Okay. And it's also the change in energy. And we know that our change in energy is our volts. I'll write this bigger. Is volts per, it actually should be a line here. Hey everybody, look at this. Is this in your booklet written like this? Okay, energy is voltage. Wait a minute, is that right? Oh no, that's right. It is VQ. A volt is a joule per coulomb, right? So if you multiply by the number of coulombs, you get the joules. Yeah.
So it's written like V equals change in EQ.
Oh. V equals change in E times Q?
Yeah.
Or per Q?
Sine times Q.
That should be like this. Volt is a joule per coulomb. So can you put this line in there? Because I don't want you to be confused by that. I'll add it to the booklet later, but that's a mistake on my part, sorry. Okay, so delta E equals V times Q. And so if you put this, if you take this volts time, and what's Q by the way? Good. Q is charge in what unit? Coulombs, right? So if you have voltage times charge and you put that in for energy, change in energy, then your power is going to be the voltage times Q over T, right? What's charge per second? That's right, Kian, good. So this is equal to VI. You'll see it written as IV. So this, we have this really well-known formula, which is P equals IV. So in an electrical circuit, you guys know you can measure current pretty easily and you can measure voltage pretty easily, right? So if you multiply the current and the voltage, that will give you the power. Anybody know the unit of power? Watts, that's right. Who said that? So a watt is a joule per second. Okay, so that was a lot. It was messy, I'm sorry. What you do is you can say, I'll post this in the video and you can look at it later, but so if P equals IV, and then we use Ohm's law, and we say, well, I would be equal to V over R, right? So if you put in V over R for the I, you get V squared over R. And if you go the other way, you would say V equals IR. So if you put in the IR for the V, you get I squared R. So these three are all usable. Okay, so if you have an electric heater and it has 100 watts when connected to a 120 volt line, what's the resistance in the heater? See if you can figure that out. We have your power is 100 watts and your voltage is 120 volts. Then we're looking for R. Which formula are you going to use? Middle, left, or right? This one? Middle?
Right?
Why the right one?
Because they have ours.
Because we have V and we have P, right? We know P and V. So if we use this one, that's going to give us R. But we're going to have to solve it, right? So we have V squared over R. How do we solve this formula for R? Yeah, you just put the R up and the P comes down. You can divide both sides by P and times both sides by R, and you're going to have R equals V squared over P. Just kind of simple three variable algebra. And so if you do your voltage squared over P, 120 squared is 14,400, and divided by 100 would be 144, right? And that would be watts. Oh no, that would be ohms. Sorry, that's resistance, not watts. Now you can do that on your calculator, you don't have to do it in your head. But that would be the answer. Okay. I think we did pretty good. pretty well. There's one more example, but we'll save that for next class. And then we'll go on and we'll do the rest. And I'll post these videos and I'll post the slides as well.